Hello everyone. Good to see you again. I hope all you are doing very well. In this video, I'm going to talk about data aggregation and its effects on analysis. Before you start, don't forget to check out our course website for if there are readings and videos required for this lecture. In this lecture, I'm going to introduce the concept of data aggregation and why we do aggregation in analysis. In marketing data, we have multiple dimensions of observations, such as individuals, markets, products, and time, which separately generate variations in data. This implies consumer demand responses to a marketing action may not be simple and must be factored into the differences in the dimensions for accurate counterfactual. However, due to various reasons, such as limited observations, it is not always feasible to consider all of the dimensions at the same time. We thus aggregate raw data at a certain level, depending on unit of analysis and unit of observation. But data aggregation necessarily leads to a loss of information. This can be very critical in some cases, where estimation results and demand predictions based on the aggregate data are biased. I'm going to introduce three classic studies that extensively discuss for the aggregation biases. Okay, are you ready? Then let's get started. Data aggregation is related to how marketing data are generated. Marketing data are generated from interactions with customers. Every day, every minute, every second, individual customers watch TV ads, search for deals, make purchases, and feedback their choices. All of those responses of customers are the sources of marketing data. That is, a marketing data set is composed of disaggregated pieces. But marketing researchers do not directly observe the raw data. Data generally used in analysis are reshaped and processed on purpose of analysis. There are several regions of reshaping data. One is granularity of analysis and decision-making problem, which is related to unit of analysis. Another reason is related to unit of observation. Disaggregate data are usually sparse, sometimes do not have enough observations to investigate effects of marketing actions. The others are duration and extent of effect. A marketing action affects not only the target specified for the action. The effect is sometimes carried over time and spilled over customers and market. Now, I'm going to talk about each of the regions in detail. First, granularity of analysis. Granularity of analysis or focus of analysis depends on research problems. For example, suppose that we want to find who is the best target of our new promotional event. The best target should be who are willing to or highly likely to react to the promotional offers. In this case, we have to predict each individual's conversion rate from each individual's responses in data. Well, how about the shelf price of a product in a store? This is more macro-level research problem. The best price should be maximizing sales, revenues, or profits from all customers visiting the store. In this case, it would be better to focus on store-level aggregate sales instead of each individual customer's demand. Moreover, how about national advertising spending? This is a real macro-level problem. National ads are on air over the states, so we need to focus on aggregate sales of the entire market, the United States. Thus, Depending on the research questions, unit of analysis must be carefully chosen, and data aggregation level must be appropriately decided based on the unit of analysis. Second, limited observations. When we look at each individual customer's data, we can easily find that they are sparse. For example, consider those two customers' purchase histories. First customer made purchases in weeks 1, 6, and 8 only, and the second customer made purchases in weeks 2, 7, and 8 only. Suppose that there were price discounts only in weeks 2, 5, and 7. Then the first customer just made purchases of the product at a regular price, implying that her purchase history may not have enough variation of prices to investigate the price effect on sales. So, in order to ensure the enough number of observations to investigate the effect of a marketing action, it is sometimes necessary to aggregate raw data over a dimension of the data. Third, duration of an effect. Some effects, such as advertising effects, could be long-lasting. For example, consider the following advertising over the week. Suppose that there was an ad on the first day of each week. The ad could boost not only the sales on the same day, but also the sales on the next several days. Then, what if we focus only on the daily effect of advertising? We may miss the effect carried over to next days and underestimate the ad effect on sales. Thus, it would be better to aggregate the data weekly and investigate the ad effect on weekly sales instead of daily sales. Of course, I don't mean that looking at weekly sales is the ultimate option. The best aggregation level totally depends on market, product, industry, and ad characteristics. Last, the extent of an effect. Some effects are not limited to a single product. Sometimes the effect could be brand-wise, tour-wise, industry-wise, and so on. For example, consider Pampers brand ads. This affects not only a single product line of Pampers. It affects various Pampers products, including its Swaddler baby diapers, baby dry diapers, Cruisers diapers, and Pampers baby wipes for sensitive skin. To correctly measure the effect of this ad, it would be better to aggregate the sales data at the brand level or the firm level. Now, I'm going to introduce three widely considered dimensions for aggregation of working data. The first dimension is customer. Market information of data depends on the level of aggregation across individuals. With individual customer level data, we can observe customer responses in granular detail, whereas we can see average trends across different markets with market level data. For example, when a manager wants to find the best target customers, individual customer level responses must be required and analyzed for the targeting practice. However, suppose that there is a manager who wants to plan the launch of a new product across multiple countries. In this case, the manager may focus on country-level summaries in order to catch common characteristics of people and important trends that potentially affect the sales of the new product in each country. The second dimension is product. Data also can be aggregated over products or SKUs. Here, an SKU is a unique identifier, such as the barcode on a product package, which is scanned at checkout. A brand usually has several different specifications of a product, and the unique SKU is assigned to each specification. For example, Colgate has a medium size of paste type mint flavored toothpaste and a large size of gel type original flavored toothpaste. Each of those Colgate toothpastes has its own unique SKU. Coming back to the main point, stores sometimes do promotion events for a wide range of products due to inventory management. In this case, store managers may focus on each SKU in the inventory. But some effect could be brand-wise or category-wise as discussed. In this case, it would be better to aggregate data at the brand level or category level. The third dimension is time. Time is the dimension which has been most widely debated in various studies. Transactions and actions with customers continuously appear every second, minute, and hour. But as mentioned before, different effects show different durations. Advertising. Each effect is usually long-lasting, whereas a flash promotion, each effect is just a couple of days or extremely a couple of hours or minutes. So, depending on the characteristics of the effects, we must carefully choose the best time level of data aggregation in analysis. For each dimension of aggregation, it always should be considered whether or not the loss of information due to aggregation possibly distorts analysis results. Data aggregation usually smooths out or averages out the fluctuations of action variables and market responses in data, so important information can be removed by data aggregation. If that's the case, model estimates from the aggregate data may be biased and lead to inaccurate demand predictions. Now, I'm going to introduce 3 classic studies that tackle the potential loss of information coming from data aggregation. Let me start with the customer dimension. Ellerby and Roshi analytically and empirically showed that the price elasticity estimate from market shares is approximately the same as the average of consumers' elasticity estimates from individual choice data. That means using aggregate models without any knowledge of heterogeneous consumer preferences can be justified for demand prediction. But the equivalence between market level analysis and the individual level analysis requires 3 conditions. First, all consumers are exposed to the same marketing mix variance. For example, the price of a product is always the same across different individual consumers in data. This is a typical situation because within a market, there is usually no price discrimination. Second, the brands are closed substitutes. This implies consumers may switch the brand from one to another depending on price and other marketing actions, and the brand switching is frequently observed in data. Typical grocery shopping items are good examples of the closed substitute. You may have your own preference on potato chips, but your choice may be frequently switched depending on coupons, price discounts, on and offline ads, and so on. Third, the price distribution is not concentrated at an extreme value. This implies, intuitively speaking, prices of products are stable and fluctuating within a bounded range. If the 3 conditions hold, aggregate level market share model provides unbiased demand predictions for price changes. This table displays results of Allenby and Ross's simulation experiment based on real market data. It is assumed that there are 8 brands in total in a market, and an aggregate linear model is fit to the market share data for each brand. The 8th brand is regarded as the outside option, so the model is fit to only the 7 brands. This column shows adjusted R-squared of the fitted model. There are 2 versions of the model. One is the unrestricted version, and the other is the restricted version. In restricted version, the model parameters are assumed to always satisfy the IIA assumption coming from a load specification. As you can see, the fitting performance is very good across all of the brands, regardless of the version of the model. As for the predictive performance, the prediction errors are quite small for both models, although the restricted version performs relatively better than the unrestricted version. Next, let's move on to the dimensional product. David Bell and his colleagues investigated if parameter estimates from attribute level share models are informative enough to successfully recover customer preferences on each SKU. An example of the attribute level share models is the brand share model, where all SKUs of a single brand are aggregated and the brand level market shares are projected on brand level, average price, and other marketing mix variables. Of course, the attribute level share models are not always informative. They are informative under several conditions. The first condition is that the product category in analysis must be well and accurately defined. For example, shampoo category data must be separated from, not integrated with, conditional category data. Second, the sets by attributes used for aggregation must be MECE, which stands for mutually exclusive and collectively exhaustive. This means there should be no single SKU included in multiple sets or excluded from all of the sets. I'm going to explain this in detail with an example in the next slide. This table is an example of attribute configurations of several SKUs in the toothpaste category. The first 7 SKUs are Colgate toothpaste with various flavors, types, and sizes. The SKU level share is the market share of each SKU. For example, the first SKU, Colgate's original flavored paste type small size toothpaste, takes 3.5% of the market. You can see that each SKU has only one level for each attribute. For example, for SKUs 1 through 7, the level of brand attribute is Colgate. Then, all of those attributes give us mutually exclusive and collectively exhaustive sets of SKUs. For example, think of groups by brand. Then, each SKU is included in a group, and no SKUs are included in multiple groups. Bell and his colleagues fit attribute level share models and SKU level share model to the data. For example, in the brand share model, the SKUs of the same brand are aggregated. The brand level share of Colgate is given by the sum of shares of all Colgate SKUs. And the Colgate share is projected onto the average price and other marketing variables of full-gate SKUs. In the study, Bell and his colleagues mainly focus on the brand intercept parameter, which is usually interpreted as the perceived value of a brand. Let's define alpha as the brand intercept. Then the brand intercept are estimated from the brand share model with the brand level market shares and brand level prices. Using the brand intercept estimates, Bell and his colleagues proposed a method to recover the SKU intercept parameter, which implies the perceived value of an SKU. That is, the value of each SKU can be simply recovered from the brand intercept estimates if the SKU level share and marketing mix information is available. These tables present their main regions. In the first table, each column displays parameter estimates of each attribute level share model. For example, the first column reports the parameter estimates of the brand share model, where SKUs are aggregated by brand. And the second column reports the estimates of the flavor share model, where SKUs are aggregated by flavors. Those very high values of adjusted R-squared implied that all attribute level share models successfully explains the choice data. In the second table, the SKU level intercept estimates are compared to the computed values from the attribute level share model. The first row reports summary statistics of the SKU level intercept estimates, and the second row presents the statistics of the SKU level intercept values computed from the attribute level share models. Difference between them is just a little, implying that model estimates from the data aggregated across SKUs are informative for consumer preferences. Last, I'm going to talk about temporal aggregation. Jerry Tellis and Doyle Weiss studied the effect of TV advertising on sales. Even though this paper was published a long time ago, but still, there are lots of debates continuing about the effect of advertising. Is it really effective on sales? Various studies have been conducted over the decades before and after this study. Those studies have used different measures of ad effect, different models, different data sets, and different data aggregation levels, which may lead to the disagreement. The authors, Tellis and Weiss, tried to address this issue with a single source, disaggregate raw data. The main finding in this article is that aggregating data over time and different consumers may cause a misunderstanding of advertising effects as having a statistically significant effect on sales. Let's see this table. This table displays regression results with various temporal aggregation levels. Columns with beta report coefficient estimates, and columns with t report the corresponding statistical significance. Roughly, if the t-value is greater than 2, we can say that the effect is statistically significant. That is, it differs from 0. These rows stand for price and promotion effect on sales. Across the different temporal aggregation levels, the coefficient estimates and statistical significance do not vary. For example, the price effect is almost the same as 0.03 in all aggregation levels. But Tallis and Weiss found that advertising effects vary across the different temporal aggregation levels. When they investigated daily data, there are no statistically significant advertising effects, whereas they found significant ad effects in weekly and monthly data. Tallis and Weiss also investigated how consumer-level aggregation changes the coefficient estimate. The left table displays an ad effect coefficient. As for each individual, both the size and the statistical significance of the coefficient vary across the temporal aggregation levels. With daily data, it seems that there is no ad effect. However, aggregating data over the individual consumers, the authors have a different result. The size of the coefficient at the market level is much bigger than that of the coefficient at the individual level. And even in daily data, the ad effect is statistically significant. The right table presents price coupon effect on sales with various aggregation levels. It is found that there is no significant difference between the aggregation levels, both in time and individual consumers. So, in sum, the ad effect estimates are affected by the aggregation levels, but the other effects are not so. Why? One possible explanation is that retailers normally don't change the promotion status of brands in the store within a week. Indeed, for most brands, the promotion variables have the same status within a month because only some of the brands go on promotion in a month. In contrast, TV ad exposures fluctuate substantially by programs and days of the week. Thus, each time the data are aggregated, the distribution of the ad variables is affected, which in turn affects the estimated coefficient. So far, I have talked about data aggregation and potential biases coming from the aggregation. Again, due to various reasons, data aggregation is inevitable in analysis. However, data aggregation generally goes with a loss of information, potentially leading to biased estimation results. And the biases become manageably small only if assumptions used for the aggregation are well justified. So, we must be cautious when we do aggregation. Alright, that's all I have in this lecture. After watching this lecture, please check out our website again for if there are additional readings and videos required or strongly recommended, online quiz assignment, and hands-on exercise in our software. Then, see you in the next lecture. Bye-bye.